Points to remember. First of all, when you enter the lab, was the burette, pipette, glass rod, glass beaker thoroughly with the tap water and then followed by distilled water. After adding the content into the beaker, each time stir well with a glass rod for homogeneity. For better homogeneity, we have to stir the solution well. And the glass rod and the electrode should not be taken out the beaker. After the end of the experiment, you must remove the electrode as well as the glass rod. This experiment is based on the principle of acid-base titration and measurement of pH using pH meter. When an acid like HCl is titrated with base NaOH, a neutralized reaction occurs. For example, HCl treated with NaOH and it will neutralize NaCl plus H2O. The pH meter is used to measure the pH of the acid solution. As the base is gradually added, as the titration progresses, the pH increases slowly at the first, then rises the sharply near the equivalent point, where the amount of base added is just enough to complete neutralize the acid. At the equivalent point, the pH changes rapidly, and the volume of Na which is added at the point is used to calculate the strength of the given HCl solution using the formula of V1N1 equal to V2N2. So first of all, we have to take sodium hydroxide in a burette, and you need to keep out 20 ml HCl. Then you need to add 20 ml conductivity water. Then the glass electrode is immersed on it, which is connected with the pH meter. Then note down the corresponding reading. NaOH is added at the equivalent point. The pH meter gives an accurate reading of the pH after each addition of base, allowing us to determine the exact point of neutralization. Then how to do the experiment? First, let wash the glass electrode with the distilled water. This remove any previous chemical residues. Always handle the electrode very gently. Then preparing the acid solution. Now take a clean 100 ml beaker. Use a pipette to measure 20 ml of the given HCl solution and transfer it into a beaker. Then add 20 ml of distilled water to it, and then this help dilute the acid slightly for better observation of pH changes. Then measuring initial pH. Now we immerse the glass electrode into the solution carefully. Ensure the bulb is fully dipped. When bulb is there, the bulb is completely immersed onto the given HCl solution. Wait for a few seconds and note the initial pH. Since HCl is a strong acid, the pH will be very low, usually around 1 to 2 pH. Now we start the titration from the burette. Add 1 ml of 0.19 NaOH into the acid solution. Use a glass rod or stir to mix it well. After mixing, wait a few minutes, few seconds, and then note down the new pH. Repeat this step. Add 1 ml. Stir. Note the pH until you a sudden jump in pH. This is the end point of neutralization. Then how to identify the endpoint? As you near the endpoint, pH will rise rapidly from around 2 to 3 to 7 to 8 and above. That sharp jump tell us acid is completely neutralized. After reaching the endpoint, add a few drops of or 1 ml of NaOH and continue nothing the pH, noting the pH for a few seconds beyond. Then plotting graph 1, pH versus volume. Now on graph paper, we plot y-axis, pH in y-axis and volume of NaOH added in x-axis. This graph shows the smooth curve at the first and then sharp vertical rise at the end point. The point of the sharp rise is the equivalent point. Next, calculate del pH by del V. After every time reading, this means every two readings, this means the change in pH per ml of NaOH added. Now we have plot another graph, del pH by del V in y-axis, the volume of NaOH in x-axis, and the peak of the graph shows the exact volume of NaOH used to neutralize the acid. This is the volume you need. From the graph, we can find out how much NaOH is needed to neutralize the given HCl. And this helps us understand acid-base titration using pH meter instead of indicator. From the table, we can find out pH of the given solution, then del pH, which indicates a change in the pH value. Del pH represents the change in the volume. From these two columns, we can get del pH by del V. From the observation, we can calculate the amount of given itself present in the given solution. Why doesn't the pH value quickly in the beginning? Because acid is very strong and very excess in initial stage. So initially pH value is very low. There are two graphs are there. In this graph, we plotting how pH of the solution changes as we keep adding NaOH to the HCl. At the first, we are adding base to strong acid, so the pH increases slowly, and the curve is almost flat. But when we reach the neutralization point where acid and base are equal, the pH rises rapidly. After that, if we keep adding more base, which means NaOH, the pH rises slowly again. So the graphs look like an S-shaped curve and sharp bend is the middle. The point where the pH jumps suddenly is called it as end point or equivalent point. This is where the acid is fully neutralized. Then graph 2, volume of NaOH is taken in the x-axis, and then del pH by del V is taken in the y-axis. This graph helps us accurately find the endpoint. We calculate how much of the pH changes after each 1 ml of NaOH added, that is del pH by del V. In the beginning, the change is small, so the graph is low. At the end point, the pH changes quickly, and the graph shows the sharp peak there. After the end point, the change becomes very small, and so the graph look like sharp peak, and the peak value tells us the exact volume of NaOH used to neutralize the acid. You have to know which graph shows the endpoint is more clearly. This graph is gives us the accurate endpoint. From this graph, we can get exact volume of sodium hydroxide is used to neutralize the HCl solution. First graph, pH by volume, shows the overall trend, slow rise, sharp jump, then slow again. From the second graph, del pH by del V and volume, help locate the endpoint accurately using the peak. Then calculation. First you have to calculate the strength of given HCl solution. So, volume of standard NaOH 11 ml, we can get it from the graph sheet. Then strength of standard NaOH, it is a given value, we can get it from the aim. And volume of HCl, we need pivotal solution 20 ml. Then strength of HCl, we have to calculate by using this formula. V1 N1 equal to V2 N2, where volume of standard NaOH, let it be 11 ml. So 11 into 0.01 divided by 20, we can get 0.0055 N. This is the normality of the given HCl solution. Then calculation of amount of HCl present in the given solution. And then the calculation of amount of HCl present in the given solution calculated using this formula. Strength of HCl, the 36.5, then equal weight of HCl, then strength of HCl, strength of HCl 0.0055 from the previous step, and the equal weight of HCl is 36.5. So combined to give us 2008 grams. So the amount of HCl present in the given solution is 0.2008 gram. Next, our experiment is estimation of ion content of the given solution using potentiometer. It is the estimate the amount of ferrous ion present in the given solution potentiometrically, and moreover, you are provided with a standard solution of 0.01 K2Cr2O7. Here, we no need any indicator. What are the main advantages of potentiometric titration? We can titrate a very dilute solution. We can titrate redox titration also. Precipitation reaction is carried out. Then we no need any indicator. It gives more accurate result. No need any keen observation required during the neutralization point. Uh, these are some advantages over the volumetric analysis. Then chemical apparatus and chemical vacuum, pipette, burette, then burette stand with the clamp, beaker, funnel, wash bottle, which contain distilled water, platinum electrode, calamel electrode, which is otherwise known as reference electrode, potentiometer, connecting wires, then graph sheet, white color porcelain tile, then the chemical like ferrous sulfate or a ferrous ammonium sulfate, standard potassium dichromate solution, sulfuric acid, and dilute distilled water. Ferrous sulfate solution. What is this is an unknown solution whose ion content we are going to estimate, and potassium dichromate. This act as the titrant and is a strong oxidizing agent used to oxidize Fe2 to Fe3 plus. And then what is the role of adding sulfuric acid? Add to maintain an acidic medium, which is essential for the redox reaction to occur properly. And then what is the role of adding distilled water? It is used to cleaning glassware and for dilution if needed. It is the setup. By the way, we have to do the experiment. It is the potentiometer. It is the electrode beaker which contains solution, the ferrous sulfate solution, and the burette we have to take potassium dichromate. And then the electrode is connected with the potentiometer. From this, we can get the potential difference of EMF reading. Then basic principle involved in this titration. The ion the ion in our solution is the form of Fe2 plus ion, that is ferrous ions. These ions can be oxidized to Fe3 plus, which means ferric ions, by using a chemical called oxidizing agent like potassium dichromate. Instead of potassium dichromate, we can get potassium permanganate also. Um, uh, we are going to perform redox reaction where this reaction takes place. Fe2 plus gives Fe3 plus electrons. As we add the oxidizing agent drop by drop to the ion solution, a chemical change takes place and the number of Fe2 plus ion decreases. Now here comes to the important point. We use a potentiometer to measure the voltage or potential difference between the two electrodes dipping in the solution. Once it is a reference electrode and another is a platinum electrode, they detect a change in Fe2 plus into Fe3 plus ratio. When the Fe2 plus ions are almost finished, just before all the converted into Fe3 plus, there will be a sudden increase in voltage. This point is called as equivalent point, and it is the most important in this titration. At this stage, we note the volume of oxidizing agent used. Using this volume and the simple formula V1N1 equal to VT N2, as we can calculate the strength or amount of ion present in the original solution. So from this principle, we can able to know we are doing a redox titration. We measure potential, which means voltage, using a potentiometer. We detect the equivalence point by the sudden jump in voltage, and finally we calculate the ion content using the titration data. This is the basic principle behind this experiment. We will now move to the procedure and setup. Before that, I'm going to explain how to draw the graph. For the first graph, we plot a volume of K2CR207 on the x-axis and EMF values on the y-axis. For the second graph, we plotted volume of K2CR207 taken in the x-axis, del V by del V in the y-axis. From the second graph, we look the maximum point or sharp peak, and the volume at this point is called as endpoint of the titration. This volume will be used in our calculation to find amount of ion present in the given solution. So that's the procedure we are going to follow. Make sure handle the electrodes carefully and uh, note your reading accurately. On the x-axis, we have the volume of potassium dichromate added in milliliters, and on the y-axis we have the EMF values measured using the potentiometer. As we started adding the dichromate solution, the EMF increases slowly at the first. This is because of ferrous ions were gradually getting oxidized. At a certain point, we notice a sudden jump or sharp rise in EMF. That sharp increase tell us that most of the Fe2 plus ions have now been converted into Fe3 plus ions, which means we are near the equivalent point or end point of the titration. After that, the curve becomes steady again as more dichromate is added beyond the reaction. So this graph helps us visually see the point of sudden change in EMF, which is close to the endpoint. Now let's move on the second graph, which is a little more precious because from the graph we can going to find out the volume of K2CR207 for calculation. On x-axis again we have the volume of potassium dichromate. On the y-axis we have del E by del V, which is the change in EMF that change in the volume. This graph shows the sharp peak and volume corresponding to the peak is considered the exact and the point of the titration. So this second graph helps us find the most accurate volume of titrant needed to complete the reaction. And we use this volume in our calculation to find the ion content. So the graph shows how the EMF changes as we add dichromate, and the sharp rise helps us to estimate the amount of potassium dichromate present in the given, ferrous ammonium sulfate present in the given solution at endpoint. The second graph, del E by del V versus volume, give us a clear peak which tell us exact volume of titration at the equivalent point. From the table, we can find out the volume of potassium dichromate used for this titration. Del E means change in the EMF reading. Electromotive force. Unit of electromotive force is yeah, milli electron volt. So what do you mean by EMF? It is a kind of driving force. It is pumped to move the electron from higher potential to lower potential. Then del E by del V, it is the which is obtained from third and the fourth column. Okay, students, now I will explain the procedure for estimating the ion content using a potentiometer. Please listen carefully and observe each step. First, we prepare 20 ml of the given Paris solution and transfer into the clean 100 ml beaker. Next, we need to add 20 ml of sodium sulfuric acid to the beaker. And this acid provides the necessary medium for the redox reaction to happen smoothly. Now we place two electrodes into the solution. One is the platinum electrode, which we connect the positive terminal of the potentiometer, and the other is the calamine electrode, which is connected to the negative terminal. When we then begin the preliminary titration, this that means we will add 1 ml at the time of standard potassium dichromate solution to the solution. After each addition, we note the EMF reading shown in the potentiometer initially, and the EMF will change slowly. At one point, we will observe the sudden jump in the EMF value. that jump indicate we are near the end point of the titration. After the jump, we still continue to add 5 more 1 ml portion, and we keep recording the EMF values for each. Now let's talk about the result of our experiment. After completing the titration and the calculation, we have finally find out the amount of ferrous ions present in the whole of the given solution. So the final result is amount of ferrous ion solution present in the whole of the given solution equal to dash gram. And the value tell us how much ion is present in the sample we were asked to analyze. Please remember, this is not just a number. It shows how we can use chemistry to determine the actual quantity of the substance in a solution. In this case, iron make sure to write this value nearly in your record notebook under heading result. Next experiment is conductor magnetic titration of strong acid versus strong base. Here we are going to titrate again strong acid like HCl versus strong base NaOH. Aim of this experiment to estimate the amount of hydrochloric acid present in the given solution by conductometrically, and moreover you are provided with a standard solution of 0.019 sodium hydroxide. Apparatus required for this titration: conductivity meter, conductivity cell, burette, pipette, beaker, measuring cylinder, glass rod, bottle which contains the distilled water, porcelain tile, graph sheet. And then chemical required: hydrochloric acid, sodium hydroxide, and distilled water. Then basic principle involved in this titration. This experiment is based on the conductivity change. As we add NaOH to HCl, ion is the solution change, and so the conductivity also changes. HCl gives HCl plus NaOH gives NaCl plus H2O. At this beginning, solution has lot of H plus ions, which has very high conductivity. When NaOH is added, uh, H plus ion gets neutralized by OH minus ions. So water is formed, conductivity decreases. At the neutral point, conductivity is at minimum. After excess NaOH, extra NaOH is increased and again conductivity decreases. So we can get V-shaped graph. Take 20 ml of HCl in a clean 100 ml beaker, then you have to add 20 ml of distilled water, and add 40, then insert the conductivity cell into the solution and connect it with the conductivity meter. Note the initial conductivity reading without adding any sodium hydroxide from the burette. Add 1 ml of sodium hydroxide from the burette and note down the corresponding reading, and then continue this until the conductivity first decreases, reaches a minimum, then start increasing. Take 3 or 4 extra reading after the endpoint. Uh, then you have to draw the table and note down the corresponding readings of conductance value. Conductance is the reciprocal of resistance. The unit is conduct mho. In this column we have to note down the volume of NaOH added from the burette. Now we plot the graph with x-axis and y-axis using volume and conductance. Volume of NaOH is added in the x-axis and then conductivity taken in the y-axis. The graph was slowed down because of H plus ions being removed, and then it reaches a minimum, that is the equivalent point. After that, it rises again due to extra OH minus ions from NaOH. Join the point with the two straight line. The point where they meet is the end point, and the corresponding volume is noted. Yes. First, initially the conductance value is very high. This is due to number of ions, and the conductivity depends upon three factors. Number one, number of ions. Number two, size of the ions. Number three, mobility of the ions. The number of ions is directly proportional to conductance. So, number of ions increases, conductance increases. Then you add 1 ml of sodium hydroxide from the burette, the conductance value gradually decreases. After getting the endpoint, then you and add if you add excess volume of sodium hydroxide, the conductance value increases. This decreasing point due to the replacement of H plus by NaOH. Since H plus is fast moving ion, Na plus is the slow moving ion. So the replacement is there. So replacement of H plus by NaCl, Na plus, the conductivity gradually decreases. Then the conductivity gradually increases by the successive addition of sodium hydroxide. Since and the volume of OH minus ion increases. OH minus ions are the fast moving ion. If the fast moving ion increases in the medium, conductivity increases. So this, so the shape of the graph tells us how the ion concentration is changing. The minimum point gives us the end point of the titration. The calculation from this calculation, as I told you earlier, from this final equation E1 N1 equal to V2 N2, we can calculate the strength of HCl. If you know the strength of HCl and the equal weight of HCl, we can find out the amount of HCl present in the given solution. And result from the equal weight and the strength of HCl, we can calculate the amount of HCl present in the given solution. Then conductor metric titration or mixture of acid using a strong base. Aim of this experiment to estimate the amount or determination of strength of given mixture of acid and strong base. And then you are provided with the standard solution of NaOH. Then basic principle involved in this conductor metric titration. This experiment is based on the change in conductivity of the solution during neutralization. When we titrate the mixture of strong and weak acid with the sodium hydroxide, different stages happen. First, NaOH react with the strong acid HCl and the conductivity decreases sharply. And then it react with the weak acid, acetic acid, which means acetic acid, and the conductivity decreases slowly. After completing the neutralization, any extra NaOH added increases the conductivity again because Na plus OH minus ions are strong conductors. By observing the change in conductivity and plotting a graph, we can determine the volume of NaOH required to neutralize each acid separately. Procedure involved in this conductor metric titration. Take 20 ml of the acid mixture which contains HCl plus acetic acid in a 100 ml beaker. Add 50 ml of distilled water to dilute it. Dip the conductivity cell into the solution. Then note the initial conductivity without adding any sodium hydroxide. Now start adding NaOH solution in 1 ml increment using a burette. After each addition, stir the solution gently and record the conductivity. Continue the process even after neutralization is complete, so you can observe the rise in conductivity. Finally, we have to plot the graph. Volume of NaOH is added is taken in the y-axis, and the conductivity is taken in the y-axis. You will see two distinct changes in slope, which help us identify two endpoints, one for strong acid, one for weak acid. Yes. And then the volume of NaOH is taken in the x-axis, and the conductance values are taken in the y-axis. Initially, the conductance value will be very high. This is due to the presence of number of ions. HCl is a strong acid, so they may dissociate into H plus Cl minus ions. So if the number of ions increases, conductance value increases. Then you add successive addition of sodium hydroxide from the burette. The conductance value gradually decreases. This is due to the replacement of H plus by Na plus, where the H plus ions are fast moving ion, Na plus is the slow moving ion. So the replacement is there. So due to the replacement, the conductivity will be decreases. Then after getting the first endpoint, if you add excess additional sodium hydroxide, it will be gradually increases. This is due to the formation of soluble salt or sodium acetate. So the sodium acetate salt is a soluble salt, so it is completely ionized into CH3COO minus plus Na plus. So the due to the formation of salt, the conductance value gradually increases. After getting the second endpoint, and if you add excess addition of sodium hydroxide from the burette, the conductance value again increases. This is due to increase in the volume of sodium hydroxide, where the OH minus ions present in the NaOH is fast moving ion. Due to the mobility increases, conductance value gradually increases. From the endpoint, we can calculate amount of HCl plus amount of acetic acid present in the given solution. Yes, from the formula, we can calculate amount of HCl as well as acetic acid present in the given solution. Then volume of NaOH from the graph sheet, then strength of NaOH from the aim, and the equal weight of HCl 36.45. From altogether, we can get amount of HCl present in the given solution. Then calculation of amount of acetic acid present in the given solution, volume of NaOH B minus K from the graph, we can get it from the graph, and which is multiplied with the strength of NaOH, which is around 0.01 N, and which is multiplied with the equivalent of acetic acid, which is around 60. Altogether, we have the amount of acetic acid present in the given solution. This experiment helps us understand how conductivity changes with the different types of acid, and how we can use it, separate and estimate them accurately using titration. Yes, then we can find out the amount of HCl and acetic acid from the previous step. Amount of HCl present in the given solution equal to dash gram, and the amount of acetic acid present in the whole of the given solution equal to dash gram. Uh, Thank you, students. That's all for today's session. Um, Please make sure you understand the aim, principle, and step for the each experiment. You will perform some of these in the lab and write the calculation result in your record notebook. Always follow the dress code and safety instructions. Thank you once again. I am looking forward to working with you in all our chemistry laboratory. Thank you once again.